So, some applications of temperature and heat. First one is thermal expansion. It turns out that most substances, when heated, will expand, and when cooled, will contract. And because of that, we have a couple formulas that we can use. We're going to focus on solids usually. The fluids we'll wait until we get to the miscellaneous topic, and we'll actually talk about how temperatures affect fluids and their volume changes. But here, with heat energy, we'll focus on the expansions of solids. And so there's a formula here for the linear thermal expansion, or how much a substance will expand when heated. And the change in length is equal to a coefficient of linear expansion, which is the value that you would either experimentally measure or look up in a table, multiplied by the initial length, multiplied by the change in temperature, or delta L equals alpha delta L naught times, or delta L equals alpha L naught delta T. Where alpha is the coefficient of linear expansion. As a side note, if you're asked for the final length of the object, you would have to add the initial length to this change in length, this delta L that you calculate here. There's also a very similar formula for volume expansion. It's just a different constant that you have to look up, and that constant is beta, the coefficient of volume expansion. Anyway, water behaves oddly when cooled. So as I said, most substances expand when heated, and water does expand when heated. But if you cool it, it contracts until you get to 4 degrees Celsius. And then at that point, it actually begins to expand again. And so because of that, it becomes less dense, and it will end up floating. So ice floats on water because it is less dense than the water itself. Most solids sink in their liquids, and so they sink down. But ice, because of this expansion, ends up floating. It's less dense than the water itself. Brings up some interesting things then with what happens to water level when the ice melts, and we'll talk about that in the miscellaneous topic. And it also is probably why life has been able to survive here on Earth. Because what ends up happening is when you have a body of water and that body of water is cooling, what ends up happening is it has to keep cooling, and as it cools, eventually it hits the 4 degrees Celsius, and 4 degrees Celsius is the densest water gets. And because of that, then, it sinks down. Now, if we could imagine that packet of water sinking all the way down to the bottom without ever getting warmed up on the way down, then it would make it all the way down to the bottom at 4 degrees Celsius. But it turns out that it probably won't make it all the way down, and so this process takes even longer than what I'm going to describe. But then the next packet of water at the surface has to cool to 4, and then it sinks down. It puts new water at the surface, has to cool to 4, and then it sinks down. And so we end up with all the water has to reach 4 degrees Celsius before it can start to freeze, because the 4 degrees Celsius water constantly sinks out of the way. So now all the 4 degrees Celsius water has sunk and the whole thing is 4 degrees Celsius, then it can start to freeze. But as it does this, it's getting less and less dense, and the colder bits then start to float on top, and you end up with ice growing across the top. And so now you have a layer of ice that's at 0, and down at the bottom you have 4, and you actually end up with liquid water underneath your ice. Now the ice will continue to freeze top down, but it also begins to act as an insulator, because the thicker that ice gets, the more it protects the cold from the outside from actually getting down to the layers underneath. And so then because of that, the ice grows down, but it begins to work as an insulator, and you usually end up with liquid water underneath. Because of that, life that's living in a lake or pond or other body of water that freezes can survive through the winter because there's still liquid there. If water behaved like almost every other substance on Earth, the ice would be the most dense part. It would sink down, and then we'd have ice, and it'd sink down, and ice, and it'd sink down, and we would freeze from the bottom up, and you'd end up with the whole body of water frozen, and only some microscopic organisms can survive being frozen like that. As a side note, in your freezer, ice freezes from the outside inward instead of top down, because it's cold all around it. The scenario I've been describing is where the cold air is above a body of water that was warm to begin with. But you still have this outside in process instead of inside out, or bottom out process like you would expect, and like we see with every other substance out there. Water is just incredibly interesting because of that. The reasons for why it expands is hydrogen bonding, which if you take in chemistry, we've talked about. Lastly, a little bit about heat engines. Heat engines are basically machines that use a heat input to do some work. And so this goes back to the first law of thermodynamics, that we put in a certain amount of heat, and some of it warms up the system, and some of it actually goes to do useful work. And an adiabatic system is a system which no heat flows into or out of the system, and that is, it enters the system and it ends up all getting used up and exiting the system again. And a heat engine is nothing more than a device that uses heat to perform work, and based off of how much work they actually do, we can calculate the efficiency of a heat engine. There's lots of different types of heat engines, and they work through a variety of different processes, and it's a topic that's just a little bit more complex than what we're going to cover here this year. That finishes up heat and thermodynamics. If you have any questions, be sure to jot them down and bring them with you to class.